Welcome to part 2 of lecture 10. Here we're going to answer 2 more problems. And they're going to be a bit more difficult, a bit more interesting than what we've dealt with so far. So here's the first one. A projectile is launched from the ground at angle theta and speed v0, is launch speed, into a headwind that causes a constant horizontal acceleration of magnitude a opposite the direction of motion. So this a here was the symbol for acceleration. It looks like this. Yeah, you know what I mean. A, magnitude a. Okay. What launch angle gives the maximum range in terms of a and g? So what do we visualize here? We visualize essentially what on the face of it might look like a projectile motion problem. You're firing a projectile at some launch angle. A little bit like the pirate ship. What's new now is that there is a horizontal acceleration, in this case due to wind, with a given magnitude a. Presumably that depends on the strength of the wind. So now we've got a situation where there's vertical acceleration due to gravity and horizontal acceleration due to a headwind. So it's no longer projectile motion, even though it involves projectile, because now both directions experience acceleration, whereas projectile motion is defined as one direction has constant velocity, one direction has constant acceleration. So in our case, both directions have acceleration. Part B is what's the angle if A. Okay, so let's do a bit of strategy here. Like, we're reading this problem, we're like, okay, what are we going to do? Actually, my first thought is when I look at B is, okay, that's just going to be plugging in numbers. So it's going to be probably going to be the easy part. Once I've solved A, B will be easy. But A is chunky. A is the substance of this, right? What launch angle gives the maximum range? Okay, so this is tricky, right? Because if you're not given a particular launch angle and told to find a range, we ask for what launch angle gives you the maximum range. So here's how we answer that kind of question. You want to find a maximum or minimum. You might say, okay, well, for a given angle, theta, what is the range? Let's call the range R for range. That is, i.e., we want R as a function of theta. So you can imagine I try all sorts of different angles, and each time I measure the range, I can essentially plot a function of the range against the launch angle, assuming that A and G they stay the same. So then I can find the maximum of this function. So this is what we're going to do first, and then find the maximum of this function. Like which angle theta maximizes R. Now, how do I do that? Well, if you know to find the maximum of y of x for some arbitrary y, then you can find R maximum of R of theta. It's just different symbols, right? Of course, if you do know how to find it, well, you probably remember it from a calculus course. So this is where we actually need to use some calculus. Okay, so let's get started on this problem. Well, let's start the way we always start. Let's start by drawing it. Oops, this is the second problem. We're going to do that in a second. Didn't know I had it there. Ready when waiting. So this is the first problem. Let me draw a picture. Here's the ground. Here's my projectile, and it's launching at some initial angle theta. And then we have it's probably going to do something like this. It's going to fly off and because it's going to be a headwind, I suspect it's going to sort of curve down a bit more than it normally would. It gets slowed down horizontally. We'll see what the actual shape is. What we know for sure is that the acceleration to the left, I'm going to use a double arrow convention, ax, and that's just equal to a. I guess I should define a coordinate system. I'm going to do that right now. So I want to have, I'm going to make this my origin. Again, keeps my life simple, right? Why not put the origin somewhere where some things are 0? Here at the beginning, our position will be 0, 0. Makes my life easy. I'm going to call this y, and I'm going to call this x as normal. So then, because x is positive to the right, I guess the acceleration is going to be minus a, because we're told the acceleration horizontally has a magnitude of a, but opposing the direction of motion, right? So it's to the left when the thing is flying to the right. Then in the y direction, of course, we have gravity, ay. Is it plus or minus? Well, y points up, or y-axis points up, so it's going to be minus g. Accelerate motion in both directions, right? So that's a new one. Okay. So what do we want to find? We want to find the range. The range is going to be this. I don't care if the shape that I drew is correct, but I can still indicate on my diagram, look, this somewhere it's going to hit the ground. That's the range. So what do I mean by range? How can we express this mathematically? Our range is, well, it's just the x position when the projectile hits the ground. I'm already thinking, okay, how can I translate the find a range into math? Ground. And when it hits the ground means, we know that from previous problems, we thought about this before, when it hits the ground, okay, that means it's again at y equals 0, right? Because when y equals 0 is the ground. Hits the ground, that is x position when y equals 0. Right, so that's it. Okay. So how can we find this? Well, I want to figure out when is y 0, and then I find that time, and I take the time and plug it into my expression for the x position. So that means I will need an expression for the y, an expression for the x. Well, they're both accelerated motion. We know how to deal with that. We've had plenty of practice. So I'm just going to write it down. X of t is going to be where we start. We start at the origin, so that's a 0, 0. And then I'm going to have the initial speed, initial x velocity. So this is v naught, it was called. It's going to be v naught cosine theta, right? Because I want the horizontal component of this, and the horizontal component is the adjacent to this angle, times t minus 1/2 a t squared. Why is it minus? It's plus half a t squared. Well, it's minus because the acceleration ax, right, is minus a. So this really could read plus 1/2 a subscript x t squared, but I'm calling a subscript x, I'm calling it a subscript x is given as minus a. So a here is a particular value of acceleration. We don't know what the value is, but it's like a given quantity. Here's a constant acceleration, the x direction, magnitude a, right? So it looks like there's some kind of general expression, but here a is just a specific value, right? So don't be confused. The minus sign, it comes from the fact that it's a headwind and it going in a positive direction just to the right. Okay, so that's that. And then for the y direction, let me think. Well, it's accelerated motion. We start again at 0. Okay, that makes my life easy. There's no zero term. And then v naught sine theta times t, because, well, the vertical component of this, right, is the opposite of the angle. And then minus 1/2 gt squared. Why? Because the acceleration is minus g, because it's down, but my y-axis points up in the opposite direction. Alright, so can we find the range? Well, the range, right, we said how to find it, we kind of figured it out already. So when is y 0? So now we're going to find the time of landing. Well, at this time, we have that y time of landing is equal to 0. So I can write 0 is equal to v naught sine theta times the time of landing minus 1/2 g t time of landing squared, right? Again, this expression applies to all t. Give me a time, you named, 10 seconds. Okay, I plug in 10 seconds here and here. I can tell you how high up the projectile is. But I know that at a particular time that corresponds to landing time, right, we again at height 0 by definition of what it means to land. So that's why I can say 0, and I plug t land in here, and I can solve for that. So how do I solve for it? Well, I can factor out, so this, it looks like a quadratic, but there's no constant term here, so I can just factor out one of those and make my life easier. I don't need to use the quadratic equation. Minus 1/2 g t land, and then the whole thing times t land. So that means if this is equal to 0, either this is 0, the math says that's an answer. Well, that's a silly answer, because time equals 0 corresponds to when we're down here. And yes, we are at height equals 0 here. The math does not lie. But that's not our landing time. It's our takeoff time, our launch time. Right, so launch time. It's not what we want. I mean, the math doesn't lie. It does tell us, hey, look, you're at height equals 0, at time equals 0. And I like, yes, I know math. Go away. So what's the other option? The other option is, of course, that this whole factor in the brackets, that's equal to 0. So v naught sine theta minus 1/2 g t, the landing time, is equal to 0. And so that means we can write down an expression for the landing time. This implies that t land is going to be equal to, let's rearrange this, to v naught sine theta divided by g. Okay, so we've got our time for the landing. So this is our time, how long the thing is in flight. So now we just have to figure out, well, where is it at that time? Where is it horizontally, the x direction? At this time. Oops, we're not doing that. Okay, so we're going to plugging it in. X of t land, that's my range, right? That's what I mean by the range. That's equal to v naught. I think I made a mistake. No, I didn't make a mistake. Sorry, I confused myself for a second. Cosine, luckily, I always keep good track of what I'm doing. You know, I annotate it, I see what I'm doing. So if I get lost suddenly, it's okay, because I can find my way again, because I annotated my own work. I don't have to start again from scratch. Okay, v naught cosine theta times t land, and then what do we have here? Minus 1/2 a t squared. So we're going to plug in the landing time here. That's a particular instant we're interested in. Let's plug those in. We're going to get v naught cosine theta times 2v naught sine theta divided by g, right? So I'm plugging in the expression I have here for here, and minus 1/2 a. Now I want to square this, so 2v naught sine theta over g squared. Okay. Suppose we should now simplify this a little bit. Let's see. So it's going. I'm going to factor out some stuff. I'm going to have 2v naught squared, and then I think that's it over g. I can factor out. That appears here and here. And then I'm left with cosine theta sine theta minus, now here I've got 4 but also half, so it's 2 which I have here, so I've got numerical factors. Then I have a over g, because the g got squared, so I've put 1g here, one is staying here, a over g, sine squared theta. So you want to double check, of course, that I did this correctly, but I'm pretty sure I have. So that's my expression for the range. Are we done? No. We were not asked to find the range. If we'd been asked to find the range, well, here we are, we found the range. But we are asked to find the maximum angle. So to find the maximum, right, this is my function r of theta. I want to find the maximum. How do I find the maximum of a function? Well, maybe, I'm not sure what this looks like, this particular function, but if I have some kind of function, here's my function, right, some kind of function like this, well, the maximum is here, and its defining feature is that it's flat. Right, that the gradient, the slope of it is 0, slope means derivative, so to find the maximum, we're going to set the slope to 0. So you've learned in your calculus course how to find the maximum of a function. Well, that's what we're doing, right? We're finding the maximum of the range as a function of theta. So we figured what theta gives me the maximum. So we have to take the derivative of this function here. Okay, it's a bit of a pain. I guess, what are we going to do? Alright, let's do it. So we are going to say that I'm going to take the derivative of this. So dr d theta. Now we start the constant out front, well, it just sticks out front. Then you've got cosine squared sine squared. Okay, you want to differentiate that. Well, cosine squared goes to minus sine, so sine theta, and sine theta goes to cosine, so plus cosine theta, cosine theta. I also have applied the product rule here. And then back here, I've got minus a over g, and then I've got sine squared theta, so it's going to apply the chain rule, right? So sine squared goes to 2 sine, and then times the derivative of sine, which is cosine. 2 sine theta, cosine theta. So chain rule from here, this one product rule to get me there. Let's see if we can simplify this a little bit. So this one is cosine squared minus sine squared. All right, so let me write this down. So 2v naught squared over g. Now this thing here, actually we don't really care about it because we're going to set the whole thing equal to 0. We'll do it in a second. So I've got cosine squared theta minus sine squared theta. That's from this term here. And then minus a over g times 2 sine theta cosine theta, and that whole thing better be equal to 0, right? Because we want to find the maximum. So we set the slope to 0. Okay, so if this whole thing is 0, well, this thing here is not 0. Right, not 0. So this whole thing must be 0. Because if I multiply A and B, well, if A isn't 0, but A times B is 0, then B is 0, right? So this whole thing must be 0. Okay, let's write this down. Let's see if we can simplify this some more. Now, in a way, we've reduced the problem to algebra, but it's sort of nasty sines and cosines everywhere. So what can I do there? Think about this for a second. So I want cosine squared theta minus sine squared theta minus A over G times 2 sine theta cosine theta is equal to 0. Well, what is theta? I can't really simplify this just, algebraically. I need some tool. The tool again is a trig identity. In fact, it's going to be 2 trig identities. And those are the following. Now, there are different ways now going here. It's not like a single line towards the target. There are different ways you could work your way through the algebra. But if I look at a list of trig identities, again, you can just go online, just type in trig identities, or you can go to the back of your textbook, in the appendix, and you find those. Well, something interesting about cosine squared minus sine squared. So you know that cosine squared plus sine squared is 1 for any angle, but cosine squared minus sine squared is equal to cosine of twice the angle. Again, for any angle, that's true. Why? Well, you could say geometry. There's a proof for it. I don't actually know it off the top of my head. It would take me some time to figure that out again. And then you've got 2 sine theta cosine theta. Now, interesting, this one here. Again, if you just look through the list, what you should find is that 2 sine theta cosine theta is just equal to, it's including the 2, sine of 2 theta. So these are the identities that relate an angle to twice that angle, right? A cosine and sine of some angle, cosine squared minus sine squared, is cosine of twice that angle. So if you have 30 degrees, cosine of 60. And same thing over here, sine cosine multiplied relating to sine of twice the angle. Right? As again, it looks funny if you haven't met this before. You can prove all of those identities geometrically, and some very interesting proofs. But right now we just accept them as a result. So now what we have is that cosine of 2 theta minus a over g is equal to sine theta, minus a over g times sine theta, that's equal to 0. Well, that's easy to rearrange. We are going to get that, let me see, so I'm going to take it to the side, I'm going to have g over a, let me do it carefully, step by step. I'm going to divide by cosine 2 theta, so I have 1 minus a over g tan theta is equal to 0, right? Sine over cosine. So I've divided both sides, left and right, by cosine 2 theta, like everything. And so I have that theta, and well, let me write out, tan theta is going to be equal to g over a. And so, oops, I made a mistake, of course, it should be 2. Let's not forget it, otherwise we get the wrong angle. So 2 theta is equal to the inverse tan of g over a. And then, as theta is going to be half of that. So this looks long, but it's all just algebra, right? So basic rearranging. Okay, and now we found the maximum angle. Found the maximum angle, this is our answer. What angle should you shoot your projectile at to get the maximum range? Well, at that angle, you plug in G and plug in A, figure out what that is. Okay, now solved, where we solved part A. Let's look at some actual, where did the problem go? We're asked to plug in some actual values when A is 0.1 of G. So if G is 10, then A would be 1, right? But it's just 1/10 of G. So part B, if A is 0.1 G, then theta is going to be 1/2 of the inverse tan of, well, G over A is just going to be G divided by 0.1 G, which is 1/2 the inverse tan of 10. And so now you can figure out what that is. So you can plug in the values and figure out what the value is in degrees. Of course, you want to make sure the calculator gives you an answer, or you find a final answer that's probably between 0 and 90, right? Because from our picture, well, we don't want to shoot to the left, and we don't want to shoot like downwards in the ground. That's not going to work, whatever the math says. The math doesn't know about the ground. So it has to be between 0 and 90 degrees. And I think that's the one you're going to get anyway, as you plug this in. And that solves it, right? So you make sure you understand every step and actually finish it off and figure out what the value is. Alright, so that was the first problem. Let's do another one. Here's our second problem, our fourth problem in total, I suppose. A child stands on a slope that makes an angle theta with the horizontal. I've drawn it down here. This is my slope, theta with the horizontal, and kicks a ball in the downhill direction. So this way, with a launch speed v0 at an angle phi above the horizontal. So in Greek, right, this is the letter phi. So phi can be written like this. You sometimes see it written like this. Those are both, they're like two versions of the lowercase phi. There are other, I don't know how this came about actually, that there's like these two sort of different ways of writing it, and even if you type it in, right, if you type phi, so you get both versions as possibilities. It's kind of funny like that. I don't know why that is, but phi, right, is the Greek f sound. So for example, if you want to say the word friend in Greek, philos, it would start with a phi. In English, that's become a sort of the ph usually, or f, depending on the word. Anyway, this is not a Greek lesson, it's a physics lesson. So the phi letter here above the horizontal, and the horizontal is not the ground, right? The horizontal is this. So let's make sure we get that straight. Okay, so how far down the hill does it land? So and again, this is in a sense a projectile motion problem, right? There's no headwind or anything like that. It's just downwards acceleration due to gravity. The issue is that, well, the ground isn't straight, isn't like horizontal. So I'm not asking, how far does it go and end up at y equals 0. I'm asking, when does it end up at down here? How can I say that in math? It hits the ground. How can I say it hits the ground if the ground is on a slope? So I want to present you with two ways to solve this problem. And no way is better than the other. There's two choices. One might be slightly faster, one might be slightly slower. I'm not entirely sure. But they, depending on also how good you are at algebra and so on, how fast you work. But they're both two ways of solving it. I'm not going to solve it for you either way. I leave that to you, and we can talk about it more in class. But I will set those two ways up for you. So the two ways correspond to essentially two choices of coordinate system. And they each have an advantage and a disadvantage. So choice 1 is that I'm going to pick a coordinate system that is like this. I don't really care right now where the origin is. I probably would place it like right there where the ball is. I'm just going to pick this coordinate system, and then I have in this coordinate system I have that ax equals 0, vx is just v naught, the horizontal component of this, cosine phi, right? This angle is the relevant one. We take the component of the velocity, and so I'd get that x as a function of time is equal to, I guess if this is my origin right here, then that would be, it would start at 0, v naught cosine phi times t, and that's it. Didn't have to squish it. I thought I had to write more. No, it's constant x velocity. In the y direction, the acceleration is, if my axis points up, it's minus g. If I chose my axis to point down, it would be plus g. It doesn't matter what you pick, you just have to be consistent. My velocity is going to be v naught sine phi, right? That's the horizontal component, sorry, the vertical component here of this velocity, and then minus g times t, and that makes the y position. I'm not going to try to squeeze this here as a function of time. Well, again, we start at height 0, I suppose. I pick this as my origin. It's going to be v naught sine phi times t minus 1/2 gt squared, because we understand accelerated motion. Okay, so that's all well and good, but then how do I express the statement it hits the ground? It hits the ground. Right, that's a tricky part in this case. That's what makes it different from a standard projectile motion problem. I'm not going to say y equals 0, because y equals 0 is this line here. Well, when the ball is over here, that's not the right point in time. How can I say when it hits the ground? And so to do this, all we have to do is we have to figure out, well, where is the ground? Where is the ground? And the ground, let me draw a little triangle here. So if the ground, let me see how I can draw this for you. So this is the ground, right? This angle here is theta. So here it go over and down. This is drawn a bit steeper than here, but it doesn't change the geometry. So this would be my x position. This would be my y position. But this is theta. This is theta. So I have the tan theta, right? It's a right angle triangle. Is y over x. Actually, this is downwards, right? So we put a minus sign there because I have to find where is it there. My y to point up, and this is going down. So tan theta is a minus y over x. The tan of this angle is this length, and this length is minus y, because y itself is negative, over x. So that implies that y equals minus x tan theta. So what I want to ask is, I want to set those equal, right? I take this and set it equal to this times tan theta. Let me just set this up. That's the time when we hit the ground. For any point along the ground, right, this relationship will hold true. It doesn't matter how big I draw this triangle. You go a certain amount over, if you go a certain amount down, those two quantities are related by this. So make sure that is clear to you. So we've got this as our condition to be on the ground, right? If the y variable raise the x variable y this, then we are on the ground. So that means we can now just put in the position of the ball. So find time to hit ground. We're going to use this one here. We're going to plug this in. V naught sine phi times t ground, t land, minus 1/2 g t ground squared is equal to minus x. X is this. It's a function of time. T ground. Then of course I can't forget the tan theta. It's squished. But let's pause a moment here, right? So this is just the expression from here at the time of landing. I don't know what it is. T ground, I don't know what it is. But I know when it lands, it is equal to minus x times the tan of theta. Right? Which I've plugged into here. I've plugged the expression for x that I have up here into the x here. Because now I'm saying, well, at the time when the ball has a y position, it relates to the x position via this, well then it must be on the ground. Then we can solve it, right? And then you can solve for t ground. And then once you've solved for t ground, well, you can plug it back into x and y. Right? So you find the time when it's the ground by solving this. It's not too difficult. And then you can plug it back into here and here to find the x and y position where it hits the ground. Like you can find the x and y position of this point because you found a time when it hits the ground. And that's the first way of solving it. Second way of solving it, maybe you should really do both ways. It's a good exercise. Like you learn a lot if you actually work through this. Ideally you listen to the video, look at your notes, and then you close your notes and you start from scratch. Make sure you can actually do this. But the second way is that we are going to pick a coordinate system that is itself tilted down the hill. So maybe I may have my x and y. I'm going to put an x bar and y bar, but just not confuse them with what we had before. Right? So I have my hill is here. I'm going to start out here, and I just pick my y coordinate system to point this way, and my x coordinate system to point this way, like down the hill. Right, so, and if I want to just draw the horizontal line here, the vertical line here, well, this would be tilted by theta. This would also be tilted by theta. It's hard to see for you, but it's all the same angle, right, just from geometry. Okay. So now what's different? Well, now it's just a projectile motion problem, right? Notice that this thing is starting out at some with its v naught at some angle phi. So it's a projectile motion problem with an initial launch angle that's phi plus theta, because that's the angle between the x-axis and v naught, and it's going, and I can see what is its range. Except one thing has changed. It makes it not really a projectile motion problem, namely that gravity pulls in both the x and the y direction. Right. So let me show this to you. Let me just draw those axes again. So this is my x bar axis. This is my y bar axis. Now gravity still pulls us down, right? Gravity pulls us straight down. Gravity doesn't care what coordinate system you choose. This is the direction of gravity. So we will be able to find components of gravity that pull us forward and pull us down. Right, so this is horizontal. Gravity acts vertical. Well, let's do the geometry here. This angle is theta, the angle of the hill. This angle here is 90 degrees, so that should make if I extend the y-axis a bit, this angle here will be theta, and so this angle inside here is going to be 90 minus theta. 90 minus theta, so that says, which then in turn makes this angle here again theta. Just from the geometry. So that means I can write down the acceleration in the x and the y direction. Notice in the y direction, right, this is my y component. This is the component here, parallel to the y-axis. So ay is going to be minus g cosine theta, because this is the adjacent to theta, or this is the adjacent to theta, depending how you want to decompose this vector here. And ax, well, it's pulling it forwards in the positive x direction, like from here, like this way, right, in the positive direction, plus g, and this side is the opposite of this, the g sine theta. So I think it's the first time we actually had to decompose an acceleration vector, in this case, the acceleration due to gravity, into components. And so now I can start from there, and I have in the x direction, I have the, well, x as a function of, x bar, excuse me, I should need to be more careful. Right, these are all my new coordinate system that's tilted. Don't want to get confused. Let's solve it both ways. X bar as a function of time is going to be, well, where I start. Let's this be the origin. Then my initial component of the launch velocity, so it's cosine, because this is adjacent to this angle. The angle is theta plus phi. And again, if this doesn't make sense to you, pause, think about it, right? This angle here, this total angle, is theta plus phi. Right, that is the launch angle in this coordinate system. Sometimes it can help if you sort of use tilted axis, you like tilt your page so it looks straight and you can sort of visualize it the normal way. Maybe a little trick just to make sure you're on the right track. So v naught cosine theta times t, and then plus 1/2 g sine theta times t squared. Then in the y direction, in the y bar direction, our tilted y direction, I'm going to have v naught sine theta plus phi, right? That is the vertical, well, not vertical, the y direction component. And this component, the vertical part, if the page is tilted like that, of v naught, the part that's parallel to the y-axis, times t, and then minus 1/2, what's the acceleration in the y bar direction, minus g cosine theta. So the minus came from t squared. So now I have those as a function of the position in both the x bar and the y bar direction as a function of time for any time. Well, at the time of landing, well, now it's easy again, because if on landing, I'm just landing on the x bar axis, so where the y bar value is 0, y bar equals 0, so I can plug 0 into here. 0 is equal to v naught sine theta plus phi times t land, I guess t ground, that's what we called it before. The time should be the same, unless I made a mistake somewhere. Minus 1/2 g cosine theta t ground. So then we solve for t ground. I'm going to let you do that. Then we take this and plug it into x bar. T ground. the expression, and you've got the distance down the hill. And you can check that that is the same answer that you got when you worked it out the first way, right? The first method where we didn't tilt our coordinate system, but we had to figure out how do I express hitting the ground if my axes are vertical and horizontal, but the ground isn't. So kind of like you choose your own difficulty, right? Choose your own challenge. Are you gonna have standard axes and, projectile motion? But the difficulty is this part here, figuring out how to say it hits the ground. Do a bit of geometry there. Or are you going to say, I'm going to tilt my axes, then that makes it easy for me to say it hits the ground, right? It's just this. But the difficulty is that I now have acceleration in both directions. I have to decompose my acceleration vector. Now, ultimately, you should get the same answer, right? Of course, it's expressed differently. Here it's expressed in terms of x bar, like the distance along the slope, whereas in the first version, you're going to get answers in terms of the x and the y value, but you should easily be able to figure out, for example, what is this length, knowing the x and y position. Just use the Pythagorean theorem, and you can compare it to this value here. And I really recommend you solve this both ways, because you learn a lot by doing it, you pick up a lot of techniques. There might be other problems where one method is a lot easier than the other, so you want to have both of those at your fingertips. Right, but both of them a little bit unusual, not your sort of box standard projectile motion problem. Alright, thanks for listening. That concludes all the lectures on kinematics. These are kinematics that we're doing in this course. And now we'll be moving on to dynamics, where we'll start talking about forces, which you can see as the causes of acceleration. I'll see you there.